Massive transformer models like GPT-4o, Llama, and Claude are the current state-of-the-art in AI. However, many of the problems we care about do not require a 100 billion parameter model. There are countless problems we can solve with smaller language models. In this video, I'm going to share one example of this by fine-tuning BERT to classify phishing URLs. I'll start by covering some key concepts, then walk through example Python code. And if you're new here, welcome. I'm Shah. I make videos about data science and entrepreneurship. If you enjoy this content, please consider clicking the subscribe button. That's a great no-cost way you can support me in all the videos that I make.
So the title of this video has a few pieces of jargon: fine-tuning, BERT, and text classification. So let's talk about each of these terms one by one. Starting with fine-tuning, this is when we adapt a pre-trained model to a particular task through additional training. Using an analogy, we can think of the pre-trained model like a slab of marble that we can refine and chisel into a statue, which in this analogy would be our fine-tuned model. And typically, the pre-trained model in this approach to machine learning is a self-supervised model, meaning that the labels used to train the pre-trained model aren't manually defined, but rather are derived from the structure of the data itself. For example, when talking about text data, we can use the inherent structure of text in order to do word prediction. We could take a sentence like adapting a pre-trained model to a particular task and simply train the model to recursively predict the next tokens. So maybe adapt would be used to predict ing, adapting would be used to predict a, adapting a would be used to predict pre, adapting a pre would be used to predict train, and so on and so forth. So the key upside of this is that humans do not need to annotate or label the training data. On the other hand, the fine-tuned model will typically be trained in a supervised way. In other words, the targets are manually defined by humans. So the reason we might want to develop a model in this way is because since the pre-trained model doesn't require any manual annotation of training data, that means we can train on much larger training data sets. We no longer have that human bottleneck. For example, BERT, which is the model we're going to be focusing on in this video, was trained on 3 billion words. In other words, we have billions of examples that this model can learn from. This is in contrast to a typical fine-tuning task, which might consist of a few thousand examples. So we're talking about 6 orders of magnitude difference in the number of examples. Today, this is the prevailing paradigm for developing state-of-the-art machine learning models. There is an initial step of pre-training, which will typically use some kind of self-supervised learning, which allows the model to learn a tremendous amount of knowledge on a massive training data set. And then the pre-trained model can be refined to be a bit more helpful through fine-tuning. Another benefit of developing models like this is that it unlocks the democratization of AI, because developing these massive pre-trained models like Llama or Mistral or Claude or GPT-4o requires tremendous resources that no individual or typical research group will be able to pull off. However, splitting the model development process into these 2 steps of first pre-training and then fine-tuning enables the pre-training to be done by specialized research labs such as OpenAI, Google, Meta, Anthropic, Mistral, so on and so forth, who can then make their pre-trained foundation models publicly available for fine-tuning. Another nuance here is that we aren't restricted to just doing one iteration of fine-tuning. Really, any fine-tuned model can serve as the starting place for additional fine-tuning. So maybe we'll take this fine-tuned model and then we'll do some additional fine-tuning to make it even more specialized for a particular use case. And this is exactly the story of ChatGPT, which was developed through 3 phases. It started with the unsupervised pre-training, then there was a supervised fine-tuning step, and then there was a final step of reinforcement learning, which refined the model even even further. That's all I'm going to say about fine-tuning in this video, but if you want to learn more, I do a deep dive in a previous video of this series. The second piece of jargon in the title of this video is BERT. Even though this paradigm of pre-training and fine-tuning models got super popular when OpenAI released ChatGPT and shared that they were able to do that through this three-step process of pre-training, fine-tuning, and then additional fine-tuning, this is an approach that's been around since at least 2015. And one of the early models that really exploited this idea was Google's BERT, which was released in 2019. BERT is a language model developed specifically with fine-tuning in mind. In other words, the researchers at Google created BERT so that other researchers and individuals could repurpose the model through fine-tuning on additional tasks. In order to do this, BERT was trained on two tasks. The first task is masked language modeling. What that means is if we have the sentence, "the cat blank on the mat," masked language modeling consists of using the context before and after this masked word, this hidden word, in order to predict it. So given this input sequence, this can be passed to BERT, and then BERT will predict what the masked word is. This is in contrast to models like GPT, which don't do masked language modeling, but rather causal language modeling, where the training task is next word or next token prediction as opposed to masked language modeling. The benefit of doing masked language modeling versus causal language modeling is that the model can use context from both sides of the sentence. It can use both the text before and after the masked word in order to make a prediction. Intuitively, this additional context gives the model more information for making predictions. But that's not the only thing that BERT was trained on. The second task that it was trained to do is next sentence prediction. What this looks like is given two sentences A and B. So here sentence A is BERT is conceptually simple and empirically powerful. And then sentence B is it obtains new state-of-the-art results on 11 NLP tasks. BERT is trained to take sentence pairs like this and output a label of is next or is not next. This is a sentence pair taken from the original BERT paper, which is reference number 1. And so this is indeed the next sentence. Alternatively, we could have a pair of sentences that are not a match. So instead we might have BERT is conceptually simple and empirically powerful. And then the next sentence is the cat sat on the mat. And so this would be not the next sentence and would receive a different label. The intuition behind having this second task of next sentence prediction in addition to masked language modeling, understanding the relationship between two sentences like sentence A and sentence B is important for downstream tasks like question answering or sentence similarity. So training BERT on these two different tasks allows it to be effectively fine-tuned on a wide range of tasks. The last thing we're going to talk about before getting into the example code is text classification, which consists of assigning a label to text sequences. And actually, the next sentence prediction task we saw in the previous slide is an example of text classification. However, there are countless other examples of where text classification might be handy. One is spam detection. So given an input sequence of text, which is a incoming email, we could develop a model to predict whether that email is spam or not spam. Similarly, if we have incoming IT tickets, we could develop a text classification model to take those text sequences and categorize the IT tickets into the appropriate tiers. Finally, one could use a text classification model to do sentiment analysis on customer reviews. In other words, to analyze the number of happy customers and the number of unhappy customers. With all the jargon covered, fine-tuning, we covered BERT, and we covered text classification, let's see a concrete example of doing this. So here I will fine-tune BERT to identify phishing URLs. This will actually be similar to to the example I shared in my fine-tuning video from last year. However, soon after posting that video, someone had pointed out an issue in that example that I had missed. And if we look at the training metrics, it's actually pretty easy to spot. The training loss is decreasing as expected. Then if we roughly look at the accuracy, it improves from the early epochs to the last epochs, but it's a bit shaky. So actually the best performing epoch was number 3, and it seems to wiggle around for the remainder of training. But the most obvious red flag is if we look at the validation loss. So this is actually monotonically increasing during training, which is the opposite of what we want to happen. So this is a clear sign of overfitting. This wasn't something I had caught, so I'm glad someone had pointed this out on the Medium article. Here I'm going to do another example where we don't see this overfitting. So for this example, we'll be using Python and the Hugging Face ecosystem. So we'll import the datasets library from Hugging Face, which gives us a data structure for loading our training, testing, and validation data. We'll import some things from the transformers library, the auto tokenizer class, the auto model for sequence classification, training arguments class, and the trainer. We'll import the evaluate library from Hugging Face, which has some handy model evaluation functions. We'll also import NumPy, which will be used to compute some of these metrics. And then we'll also import this data collator from the transformers library, which we'll talk about in a little bit. With our imports, we'll load our data set. So this is something I've made freely available on the Hugging Face hub. It's a data set of 3,000 examples, 70% of which are used for training, 15% of which are used for testing, and then the final 15% are used for independent validation. With our data loaded in, we can load the pre-trained model. So here we're going to be using Google's BERT, more specifically BERT base uncased, which consists of 110 million parameters, which by today's standards is tiny, but at one point this was a pretty big model. We'll load in the tokenizer for this model. What this will do is take in arbitrary text sequences and convert them into integer sequences based on what the BERT model is expecting. Finally, we can load in the BERT model, but slap on top of it a binary classification head. So all we have to do is use this auto model for sequence classification class and use this from pre-trained method. And we'll pass into it the model path, which is what we defined here, the number of labels, the number of classes, and then a mapping for the classes. So the ID is going to be an integer, and then we'll have a label for each class. 0 will correspond to a safe URL, and 1 will correspond to a unsafe URL. With our model loaded in and our classification head slapped on top of it, let's set the trainable parameters. By default, when we loaded in our model in this line of code, it initializes all the model parameters as trainable. So all 110 million parameters plus the parameters in the binary classification head are all ready to be trained. However, if you're just running this example on your laptop like I did, that's going to be pretty computationally expensive and potentially unnecessary. So to help with that, here we're going to freeze most of the parameters in the model. We can do that pretty easily. So here I have a for loop that's going to go through the base model, and it's going to freeze all the base model parameters. To just break this down a little bit, we have this model object, which has this base model attribute, and then that base model attribute has this named parameters method, which will return tuples corresponding to all the parameters in the model. Basically, what we can do is go through all the base model parameters and set this requires grad property to false. After running this, all the base model parameters are frozen, and only the parameters in that classification head that we slapped on top of the model are trainable. Another name for training a model like this is called transfer learning, where we leave the base model parameters frozen and only train a classification head that we add on top of it. However, this might result in a pretty rigid model because we can only refine the parameters in that classification head. So one thing we can do is we can unfreeze the base model parameters in the final 2 layers. So in the pooling layers of this model. One way we can do this is that we can loop back through the base model parameters, and then if we see the word pooler in the name of the model, we can just unfreeze those parameters. The result of all this is that we freeze all the model parameters except for the last 4 layers. This allows us to keep the computational cost down for fine-tuning while also giving us a fair amount of flexibility. And of course, you can freeze or unfreeze any of the model parameters that you like, and this would be like a fun thing to experiment with on your own. With our model ready to be trained, next we need to pre-process our data. This is actually going to be pretty simple. We'll define a function called preprocess function, which will take in an arbitrary sequence of text and tokenize it. So it'll translate a string of words into a sequence of integers according to the BERT tokenizer. Additionally, I add this truncation flag. What that will do is ensure that none of the input URLs are too long. So by default, I think this will truncate all the input sequences to 512 tokens. And then with that function defined, we can just apply this pre-processing step to all the data sets in our dataset dictionary that we imported earlier. So this will tokenize the training, testing, and validation data sets and return it in this tokenized data variable. And then another thing we can initialize at this point is a data collator. And so we took care of input sequences that might be too long, but when we are training a model, it's important that every example in a batch is the same size. And so even though we won't have any examples greater than 512 integers, we will have examples with fewer than that. So to ensure all the examples in a batch have a uniform length, we can create this data collator, which will automatically do that for us during training. Okay, and then the final step before we actually train the model is to define evaluation metrics. These are the metrics that will be printed during the training process. Here I'll use 2 evaluation metrics, the accuracy and the AUC score. These are both loaded from the evaluate library. Then I will define this function called compute metrics, which will compute the accuracy and AUC score for any example. So the input of this function will be a tuple. It'll consist of predictions and labels. Predictions will be a logit. It'll be a number between -1 and 1, while labels will be the ground truth. So this will be either 0 or 1. To convert the logits into probabilities, so basically to map a number between -1 and 1 to a number between 0 and 1, we'll apply the softmax function, which looks like this. This will compute probabilities for both cases, for both the URL is safe and the URL is not safe. So let's only look at the probabilities for the URL being not safe. And then we'll use that to compute the AUC score. We do that by passing in the positive class probabilities, so the probability that the URL is not safe, and the ground truth, and we'll round it to 3 decimal places. So that gives us our AUC score, and then we can predict the most probable class. So predictions will consist of 2 numbers. It'll be a logit corresponding to a safe URL and the logit corresponding to a unsafe URL. We'll just do argmax, so it'll just return which element is larger, and then we can pass that into this line of code to compute the accuracy. So we'll compare the predicted class with the ground truth, and we'll round that number to 3 decimal places. Then we'll return a dictionary, which consists of the accuracy and AUC score. While this may have been a lot of hoops to jump through, this will be nice during training because at each epoch, our trainer will print out the accuracy and AUC score for us. Now we're ready to start training the model. We'll define our training parameters. We'll set the learning rate at 2 to the -4, batch size as 8, and number of epochs as 10. We'll put all these into a training arguments variable. So we can set our output directory, which I set as BERT Phishing classifier teacher. The reason this teacher is here, we'll talk about near the end. We'll set the learning rate defined here. We'll put the per device training and evaluation batch size, which is just going to be 8. Number of epochs is 10. And then logging, evaluation, and save strategy. So logging strategy sets how often the trainer will print the training loss. Eval strategy sets how often the trainer will print the evaluation validation metrics that we defined earlier, so AUC and accuracy. And then we can also set our save strategy. So we can have the model get saved at every epoch just in case something goes wrong. We can refer back to that latest save. And then we'll set that the trainer will load the best model at the end. So if the 10th epoch isn't the best model, maybe it was the 8th epoch, we'll use that one instead of the last one. With all the training arguments set, we are ready to fine tune our model. We'll pass everything into our trainer, pass in our model, the training arguments from before, our training data set, our evaluation data set, the tokenizer, the data collator, and the compute metrics function, and then simply run trainer.train. So this I think took about 15 minutes to run on my laptop. Didn't use a GPU or anything, but here are the results. We can see the training loss is steadily decreasing. We see the validation loss is a little rocky at times, but it eventually goes down. And then we have our accuracy in AUC. So we can see the accuracy is for the most part increasing, and then the AUC is steadily increasing. So this is what we want to see. We don't want our validation loss to be monotonically increasing. We want it to be decreasing with training. But we can go one step further. This is evaluating our model on the training data and the testing data, but let's look at it on the independent validation data set. This validation data was not used for training the model parameters or tuning the hyperparameters, so it gives us a fair evaluation of the model. To apply the model to the validation data, we'll generate predictions for it like this. Then we will extract the logits and the labels from the predictions, and then we'll just pass these into the compute metrics function defined earlier, and then we can see that these are the results. The accuracy and AUC score are comparable to what we were seeing for the testing data set in the previous slide. So accuracy about 0.89, AUC about 0.95. If we go back, we see accuracy 0.87, AUC 0.95. Pretty similar. So that's a good sign that this model is probably not overfitting. At the end of this, we have a binary classification model that consists of a little over 110 million parameters. However, as a bonus, we can actually shrink this model even further. And that's exactly what I do in a previous video of this series, where I talk about model compression for large language models. The example in that video, I take the model that we just created here and reduce its memory footprint by 7x using model distillation and quantization. The key upside of these compression techniques is that we can shrink the computational requirements for our models without sacrificing performance. In fact, for the example that I walked through in this video, the performance actually goes up a little bit. That brings us to the end. If you enjoyed this video and you want to learn more, check out the blog In Towards Data Science. There I cover some more details that I may have missed here. And even though this is a member-only story, you can access it completely for free using the friend link in the description below. And as always, thank you so much for your time, and thanks for watching.